Hyperbolic functions. Hyperbolic functions. Here we want to develop the properties of hyperbolic functions to show how to differentiate and integrate hyperbolic functions. The two basic scenarios, the definitions of hyperbolic functions, is based on the hyperbolic sine x and the hyperbolic cosine x. They are defined here in terms of the exponential form. Hyperbolic sine x is e to the x minus e to the negative x divided by 2. Hyperbolic cosine x is e to the x plus e to the negative x divided by 2. All of the other forms are derived, the other four are derived from the two there, hyperbolic cosine, hyperbolic sine. Various hyperbolic identities, very similar to the identities for the regular trigonometric functions. Here, our goal is to discuss the derivatives and the integrals of hyperbolic functions. There are a lot of formulas here that you would know, and so as you are aware, on this test you are allowed to use the formula sheet that I have provided in Blackboard for you. The derivatives of the 6 hyperbolic functions here are very similar. The only difference is in terms of those negative signs, and the way I keep this in my head is that the derivatives of the 6 hyperbolic functions are similar to the derivatives for the trigonometric forms. However, for the basic, the 3, the hyperbolic sine, hyperbolic cosine, hyperbolic tangent, those derivatives are positives. And then for the other 3, the derivatives of hyperbolic cotangent, hyperbolic secant, hyperbolic cosecant, those derivative results are negative. And then going over to the integrals, basically the same setup here. The antiderivative gives you back what you started from the derivative, and then that is for hyperbolic cosine, hyperbolic sine, hyperbolic here secant square u du, integrate that, we get the hyperbolic tangent, very familiar. So those 3. Then the last 3, take the negatives and apply as you did in just the reverse way with respect to the derivatives, then going to the integrals. Well, there's one more set of formulas, and here are the formulas for the inverse hyperbolic functions, whether we talk about the derivatives or the integrals. And for these, who keeps that stuff in their head? I know I don't, so we have to refer, whenever we have a problem, to some kind of formula sheet. Well, let's look at some problems. I think most of them are very straightforward. I've tried to be direct with the problems here that I've given you. So we find f prime of x So f prime of x would be the derivative of the hyperbolic sine, which is hyperbolic cosine, then times the derivative of 3x, which is 3. Just write that first. 3 times the hyperbolic cosine of 3x. So the chain rule and the power rules of regular differentiation applies still with the hyperbolic functions. So this next one, f prime of x, is equal to, well, we know that the derivative of the natural log of a term is 1 over that term times the derivative of that term. So here this is 1 over hyperbolic sine x times the derivative of hyperbolic sine x, which is hyperbolic cosine x. So f prime of x is equal to hyperbolic cosine x divided by hyperbolic sine x, which, to keep saying hyperbolic, you got to have some oil and grease in your jaws, right? Of which I do lack. So this is simply the hyperbolic cotangent x. Y prime. First part, we use the product rule, so the derivative of the first is 1 times the second plus the first times the derivative of the second, then minus, now this derivative is hyperbolic cosine x. So y prime, these terms cancel. It's just x hyperbolic sine x. Now let's look at the integrals. You'd have to use a u du substitution. Let u equal to 2x. So du is 2 dx. So 1/2 du is dx. So this is 1/2 times the integral of hyperbolic cosine u du, which becomes 1/2. The integral of hyperbolic cosine is hyperbolic sine of u plus c, and so your answer is 1/2 hyperbolic sine here of u, and u is 2x plus c. Again, we'll use a u du substitution. Let u equal to the square root of x. So du is 1/2 times x to the negative 1/2 dx. So 2 du is equal to 1 over the square root of x times dx. So what that gives us then is a 2, the integral. Notice that dx divided by the square root of x becomes 2 du. So we can represent this dx and this radical downstairs with these two terms here. This is the integral 2 times hyperbolic cosine of u du. And this gives us 2 times the hyperbolic sine of u plus c. And so our answer is 2 hyperbolic sine. Here, u is the square root of x plus c. Well, this looks like a natural log. Let u equal to hyperbolic sine x. Well, du is hyperbolic cosine x. This is the integral of 1 over u times du, which is the natural log of the absolute value of u plus c. So this is the natural log of the absolute value here of u, and that's hyperbolic sine x plus c. Now there's two more problems dealing with the inverse hyperbolic cosines. Well, we need the formula for the derivative for the inverse hyperbolic cosine x. Do you remember what that is? So the derivative for the hyperbolic cosine, the inverse of that, is u prime divided by the square root of u squared minus 1. So here, this becomes u prime all over the square root of u squared minus 1. Now, here, u is equal to 3x, right? And so u prime is equal to 3. So here, this y prime is the u prime, which is 3 all over the square root of u squared, which would be 3x to be squared minus 1. And that just gives us 3 all over the square root of 9x squared minus 1. Now, for this one, we need the formula for the derivative for the inverse hyperbolic sine. Well, it's this expression here. So that's u prime over the square root of u squared plus 1. For our problem, u is tangent x. So u prime is equal to, well, y prime is equal to u prime all over the square root of u squared plus 1. For this problem, u is equal to tangent x. So if that's the case, then u prime, the derivative of tangent, is secant square x. This is all over the square root of u squared, which is tangent square x plus 1. Well, tangent square x plus 1 is secant square, so this is secant square x divided by the square root of secant square x. So this is secant square x divided by the absolute value of secant x by definition. Let's see if I can. And so y prime is equal to the absolute value of secant x. Based on that denominator here, the secant x must be positive. But I think that'll do it. Thank you.